Action.
Action. So what we're going to do is try and apply some of our simple harmonic motion concepts to write down an equation for the period of a pendulum. What are the forces acting on the pendulum when it's there? What are the forces acting on the pendulum?
Gravity.
Gravity. Tension. Upwards. We've got gravity going that way, and we have got tension going that way. And which way is our pendulum going to swing?
Probably right.
So we know that the net force is going to be that way. We can kind of make sense of this by drawing the gravity down and the tension up, and there goes our net force. That string can't break, so the net force has to be at right angles to the tension. This is Fg equals mg. This is our F net here, and this is an angle here. Look at that, that's an angle, that thing. And so what we are going to spot from our angle there is that the net force we can find out, can't we? If we know like the gravitational force, we can work out what the net force is. How do we do that?
Trigonometry.
Yeah, which one?
We're trying to find sin.
Yeah, sin. It's the opposite side. So here we've got mg sin theta. And if we're interested in the acceleration, because we're often interested in the acceleration, we can just apply our F equals ma and rearrange it to A as F over m, and be like, we just need to cancel that m out of that equation, and we're going to get A is equal to G sine theta. Let's have a think. Let's have a think about that theta for a little bit. Just bear with me. It's the same angle that we swing the pendulum at, and that pendulum might be a length L, and the displacement, that's like an arc. When you displace a pendulum, you displace it through like a curve. And so we know from our definition of like what a radian is that the theta must be y upon L, because the angle is just the arc length over the radius, and the radius of that circle is just the length of the string. And so we know that theta is y upon L, and some of you might remember that when the angle's really, really small, theta, sine theta, same thing, right? And so acceleration, we can just call it g theta, and theta is y upon L.
No.
So we've got acceleration is g y upon L, but simple harmonic motion. A equals minus omega squared y. Spot any similarities?
Yeah, A and Y.
A and y and the minus sign. What's omega?
Angular velocity.
Square root of.
It's
Omega.
thing turned over seconds.
Yeah, check this little puppy dog out. Omega squared is g upon L. Except we don't really want to have omega squared. We want 2 pi over t squared is g upon L. And we're trying to find the period of the pendulum. So let's get that t on the top by doing the flip both sides. So t upon 2 pi squared is L upon g.
Why?
No squares. T over 2 pi is square root L upon g. And finally, let's get that 2 pi out of here. T is equal to 2 pi square root L over g. That's on your formula sheet. Check this out. The only thing that the period of a pendulum depends on is the length of the pendulum and the acceleration due to gravity. It doesn't depend on the size of the swing. It's one of these cool things that comes out of simple harmonic motion. However, beware of that assumption we made along the way, that small angle assumption, that sine theta is around about equal to theta in radians when the angle is small.
Would you say small is classified as like less
10 degrees or less-ish.
Done. Done deal. 10 or less.
And so the skill, what we did is we wrote down an equation that had acceleration and displacement in it, and then compared it with our fundamental equation for simple harmonic motion, and used that to write that comparison to see that omega squared must be g upon L. And we used that to write down a period equation. That is the common thing that's going to come across.